So we were just talking about why do we need to push forward when we make a turn, and what's happening to our needed or required lift when we make a bank. This is our delta wing, and this delta wing weighs 1,000 pounds. We need, in order to fly straight and level and hold ourselves up, we need to make 1,000 pounds of lift. There's two ways we can make 1,000 pounds of lift. In our case, we can make 1,000 pounds of lift at our bar trimmed neutral at 50 miles per hour. And that's going to take a certain amount of power to fly at that speed. Or we can push the bar forward and slow down to say 45 miles per hour and reduce the power maybe a little bit and still make 1,000 pounds of lift. Now, when we got a 90-degree angle right here. That's a 90. We have the ground, we got a 90 degree here. Okay? So that's important to understand. Our vector of lift is vertical. It's our vertical component of lift. Now we take that same exact scenario, we got our wing, and now we're in like a 45-degree bank angle here. And we're going to call this 1,000 pounds of lift. That distance there, you get a tape measure, I might not be exact. So there's our 1,000 pounds of lift. It doesn't get down to the ground anymore. So this is 1,000. That's not enough to hold us up. This is a geometric equation. And now we can come down. We're going to hit that at 45 degrees. And we've got another 400 pounds of lift. So in a 45-degree bank turn, we need something like, I'd have to do the exact math, but it's around 1,400 pounds of lift to hold up a 1,400-pound aircraft in a 45-degree bank turn. Now we go to a 60-degree bank, which is going to look like this. And we're going to need, well, there's 1,000. That's not even getting close to the ground. It's 1,000 pounds of lift again. And now it's going to take another 1,000 pounds of lift to get down to the ground in our 60-degree bank turn. And so we've got to be prepared to make 2,000 pounds of lift with our wing if we're going to bank to 60 degrees. And if we can't generate that because we entered the turn too slow, we don't have enough energy to release to create that 2,000 pounds of lift, this aircraft is going to go down. Likewise, if we're in a 45-degree bank turn and we push out hard enough or we give it throttle or a combination there of the two, and we start producing 2,000 pounds of lift, this is going to be an ascending turn. It's going to actually start to climb. Okay? And the way that we know how much lift we need to make is going to be based on looking at the horizon, and if our nose is above the horizon or below the horizon. And any time that your nose is below the horizon, when we're trying to make a level turn, you should know we're descending and you're not producing enough lift for that particular bank angle. All right, and then the last thing we were talking about is there's two ways to, well, there's a few different ways to make that extra lift, but that lift is going to come as a combination of our power setting and our angle of attack. And we can do any kind of combination of those two things to get that extra. But it's important that if you are going to go to 60 degrees and the trike that we're in, we can't do it from cruise speed. We've got to energize the wing by pulling the control bar in before we can roll to 60 degrees in bank and release that energy and create that 2Gs. So if you weigh 160 pounds and you've got a scale underneath your butt, that scale is literally going to read 320 pounds. And the wing does not know that it's not just carrying 2,000 pounds of load. G-force times weight is all the wing knows. So we literally have to make that 2,000 pounds of lift the same as if we took off at 2,000 pounds straight and level to fly in level flight.
Well, we're going to lose airspeed unless we add throttle, correct?
No. So the reason that we lose airspeed when we push the bar forward, so here's our little delta wing flying along at its normal angle of attack. We're going forward. And we push the bar forward. What's going to happen to our flight path is it's going to go up initially. Okay? We always say pushing the bar forward is a temporary solution to a long-term problem if you want to climb. Well, when you push the bar forward, you do get a sense of, oh boy, look at this, I'm going up. But what's happening to our airspeed when we go up and we haven't changed our power setting?
You're actually slowing down.
We're absolutely slowing down. And because we're slowing down, the next part of this phase is it's probably going to start to go this direction.
Right.
Now, that's with the wings level when there's an increase of angle of attack and no power setting change. However, when you take this trike over here, that's got our wheels, I'm trying to do a 3D drawing here, and we're sitting in this, flying it with our A-frame, and now we start increasing angle of attack, we start increasing to 1,400 pounds of lift, but our flight path from the side now is straight. We're trying to make a level turn. So what's the real reason that the aircraft slows down when we push forward? Sure, there's the induced drag, and once this stabilizes out, by the way, which may do something like this, we will be at, say, 45 miles per hour, and it may be still going straight and level. It might be climbing slightly. It might be descending. So we have a higher drag. But the thing I want to talk about is that when we're in this turn, this aircraft now weighs 1,400 pounds. So I didn't cover this in the air. But the reason that we're still at 50 miles an hour with the control bar out is twofold. One, the aircraft isn't climbing. It's not climbing because it needs that higher angle of attack in order just to maintain level flight. So we don't have gravity slowing us down, creating this dynamic pitch stability. The other thing is, when you're in a 1,400 pound aircraft, it's going to fly faster. You know, if you think about it, we're flying, say, a 15-meter wing on our Revolt, which weighs 1,000 pounds. It goes 50 miles an hour. When we put that 15-meter wing on a Rev that weighs 600 pounds, it goes 40 miles an hour. Same angle of attack. So the more weight you have, the faster the aircraft is going to go at the same angle of attack. And that's why you noticed that when we were at a higher angle of attack, not only were we not opposing gravity and getting into this phugoid oscillation, but we were also maintaining 50 miles an hour, and we didn't slow down for two reasons. We weren't climbing, and we weighed more. And because we weighed more, the aircraft didn't even slow down. And if you would have reduced the angle of attack back to trim, the aircraft would have started in on a spiral descent. So, and you would have seen the nose drop below the horizon, and you would have known as soon as the nose dropped below the horizon that you need to do one of three things: add throttle, add angle of attack, or reduce bank angle and return that vector of lift towards the earth so we can get it. So you can get it one of three ways. And then the last thing I'll end on, because I can't talk about this too much, is in a spiral descent, when the nose is low, adding throttle and adding angle of attack will bring the nose up. So the things that keep you out of entering the spiral dive are also the things that'll lock you into a spiral dive. Once you get into a spiral dive, adding angle of attack and adding throttle will actually increase your rate of descent and your rate of turn towards the ground. So the best way to stay out of a spiral dive is to make sure that the bank angle that you're going to go to is an acceptable bank angle, that you have enough airspeed to be able to produce the needed G-force for the turn. If you're going to 60-degree bank turn, you need to know that you're at an airspeed and your wing is energized enough to be able to produce 2,000 pounds of lift and double its lift as you're entering this turn. Otherwise, it will inevitably turn into at least a spiral descent. And then even in a spiral descent, if you give it enough throttle, you can bring the nose back up in many cases. But at a certain point, if it go about 30 degrees nose down, about 60 degrees in bank, once you cross over that threshold, adding more throttle and more angle attack will wind you into the spiral. So the best way to stay out of the spiral is keep your eyes on the horizon and not ever let the nose come down. And of course, You can only do that if you have enough airspeed and energy in the wing to be able to create the lift that you need. So 45-degree bank turn, you're going to need about 40% more lift. A 60-degree bank turn, you're going to need 200% more lift. And of course, if the wing is sideways in a 90-degree, how much lift do you need to be able to hold the aircraft up in a 90-degree bank turn?
Huge.
Infinity.
Yeah.
And infinity isn't even enough. You can't. Right. That's right. That's exactly right. So this never intersects the ground. So the lift required as you bank is exponential. So, a little baby bank takes almost nothing. 15, 20-degree bank turn takes nothing. That 45 takes so much more G-force. And then by the time you go 60 degrees, it takes so much more G-force. And then you go to 70 degrees, there's not many trikes that can do a 70-degree bank turn and maintain altitude. When you see a trike that's gone to 90 degrees in bank, what they're doing is a parabolic, kind of like this. So when you have an upline, and aerobatic pilots use this all the time, you can turn the delta wing sideways because it doesn't need to make any lift because the aircraft is more or less weightless at the top of the arc. So you see something in a trike
but
where
you can't hold that for...
You can't hold it.
Right.
And furthermore, you're coming out of the bottom of this, generally speaking, in a spiral dive that needs to be recovered. Otherwise, you're into that spiral dive, and we actually have some video of somebody doing the parabolic arc, coming out as expected, and then continuing to spiral into the ground. So that spiral recovery and just understanding these things. I know I've made a mess of this board now, but that's why we got to push forward. That's why the aircraft doesn't slow down. And if you don't push forward, it's going to definitely lose altitude. So if we pull the controls in to make the turn, we can release out, and we're nowhere near stall. We're back here. If we move the bar sideways, now we're pushing out here, and the nose drops. If you push more, you can stall a wing, and you're into that spiral dive. And how do we get out of spiral dive? High hand to hip. Don't ever forget it. Spiral dives remain the #1 reason for fatal crashes worldwide when it comes to trikes. The topics that we covered in this video, I believe, are the key to staying out of the spiral in the first place. If you fly a trike and haven't had spiral training, please seek that training. If you enjoyed this video, please subscribe to our YouTube channel. And if you'd like to learn more about trikes or already fly trikes, check out trikeaction.com, where the action is.